that to me was kind of, I don't know if I would call that a wake-up call, but certainly a major surprise. Back then, I was educated with the belief that supervised learning and backpropagation through neural network was a no-go for biology. Your feed-forward visual system has potentially anywhere from 2 to 3 orders of magnitude less layers of processing than the state-of-the-art in deep learning. This is just the beginning, and this is opening up doors that I haven't seen open until now.
This is Brain Inspired.
Hey everyone, I'm Paul Middlebrooks. Today I'm bringing you someone straight from the cauldron of visual neuroscience and AI. Thomas Serre runs his computational neuroscience lab at Brown University. These days, Thomas is working with deep learning type networks to model various aspects of visual processing. One of his main thrusts is to figure out exactly what all the brain's recurrent processing is good for. So we know that feed-forward models like convolutional neural networks are good at object recognition. And some of Thomas' work has shown that there's an initial feed-forward sweep of visual processing in our brains that can do the same thing. But we also know there are lots of cognitive functions beyond object recognition, and there are lots of loops in the brain, giving rise to recurrent connections both locally in a given brain area and across brain areas with feedback-type projections. So we talk about some of his current work showing what recurrence can do for us, for our brains, and what it can do for deep learning networks. And we cover some of his other current projects as well. We also talk about Thomas' history a bit and the history of modeling visual processing. So Thomas worked on the well-known HMAX model of visual processing in Tommaso Poggio's lab, and he spent much time and effort building in biological constraints into the model. And I think you'll enjoy his stories about deep learning sort of coming onto the scene, and before that, his interactions with some of the people who were working on early convolutional neural network models. It's an interesting tract in history in these subjects that hopefully someone is documenting out there. Thanks this week to Wojciech, Frederick, Yolande, Kasia, and Lana for your support on Patreon. You'll be hearing from me soon. Find the show notes at braininspired.co/podcast/65. A link to some of Thomas' recent work and also some excellent reviews that he's recently written about the things that we discuss. All right, I have to go teach my youngest son how to read now. It's a very different sort of challenge. Hope you're doing well out there, and I hope that you enjoy my conversation with Thomas. Thomas, thanks for joining me here. I know that you guys are on lockdown at Brown, so thanks for, and things are probably kind of chaotic right now, aren't they?
Well, we're getting ready for transitioning to online courses, and so there's a little bit of chaos, but it's manageable.
Well, thanks for taking the time. So, all right, you've worked on computer vision for a long time, and hierarchical models of vision in brains. Like for instance, you worked on HMAX, the HMAX model, which is one of the most recent precursors, sort of to deep networks. And you used HMAX for a variety of things, for instance, rapidly categorizing visual objects. And so I'm going to ask you a question, and maybe as a point of reference, you can kind of describe what HMAX is for people who haven't studied it in depth. Because my question is, what's your overall take on this recent burst of deep learning?
So HMAX is essentially the product of many years of research in the Poggio lab, which is where I did my PhD at MIT. Tommy Poggio is one of these kind of, I guess we can call him one of the grandfathers of computational neuroscience.
Does he like to be called that?
I don't know. I'll ask him.
Yeah, I'll have him on sometime. Hopefully, I'll ask him too.
That'd be great. And he did a lot of work, seminal work on statistical learning theory in the 90s. Kind of back then the work was focusing on what by today's standard we would call shallow architecture, shallow neural networks, things like support vector machines, radial basis functions, but really all the theory that lay down the groundwork for the field of machine learning, modern machine learning. And what is interesting, I think, about the work that Tommy has done is that Tommy slowly transitioned from a focus on support vector machine and those shallow architectures towards moving in a direction that essentially turned those architectures into more hierarchical kind of fit-for network models. And this is the work that he did with Max Riesenhuber in the late 90s. So I would say, and so really I joined the group studying my PhD in 2001. And I joined Tommy's group because I was very, very excited about the work that was going on back then. So HMAX was this kind of exciting but also highly simplistic kind of model of the ventral stream of the visual cortex. To me, what was exciting about HMAX was that it showed the potential of trying to build computational models that would be able to explain the response properties of neurons in specific areas of the visual system. But back then, I was an engineering student back in France, and I remember looking at this work and thinking, there's a lot of engineering and kind of handcrafting in this neural network that, it's not clear, I think the selectivity of neurons in intermediate areas was essentially built by hand so that neurons would respond to very simple combinations of orientations. And, the recognition was tested on the same kinds of stimuli that were used on for the monkey electrophysiology, things like paper clips and, kind of simple black and white stimuli. But as I remember, as an engineer and a student interested in computer vision, I was convinced by the neuroscience, but I was not really convinced by the application and, the demonstration that potentially this neural network could solve complex visual recognition tasks. And so part of the reason why I applied to MIT and wanted to work with Tommy Poggio was really to try to bring in my expertise and background in computer vision to try to take this model to the next step and really try to see how far we could go towards getting this kind of somewhat toyish computational neuroscience model of vision into a model that could solve complex visual recognition tasks. And back then I was interested in face recognition and detection. And so some of the first problems we tried to tackle was how to extend this model of neuroscience, what's missing in this model of neuroscience to try to get it to work on more complex problems. And something that I forgot to mention is that, when I started, I took the HMAX, tried to solve a face detection task, and the network was at chance, right? So that was kind of disappointing. But this was the focus of my PhD, and working closely with Max Riesenhuber and Tommy Poggio, we kind of took the model, extended the model towards a more realistic model of biological vision by adding additional constraints derived from neurobiology and the anatomy of the visual system. So this ended up with a network that had more units, that was a little bit deeper than the original model, etc., more constrained by biophysical data.
But you came in with a less biological background?
I came, applied for the PhD in neuroscience at MIT with zero neuroscience background.
But you're saying, so just in retrospect, you saw it and you thought, well, the biology is fine, but I need to bring a better engineering perspective to it. But
that's correct.
So how did you judge the biology of it without a...
Well, I guess I to be fair, I don't think I was in a position to really judge it. But the fact that it's published in, Nature Neuroscience, and the fact that the model was really able to reproduce some of the, what appeared to be back then, the key properties of neurons in the inferior temporal cortex. I was willing to take that at face value and, seeing the potential of, mechanistically accounting for neural responses.
Gotcha.
But trying to make this architecture work on more complex kind of stimuli. And then again, when I joined, the model appeared not to work very well for more realistic stimuli like faces. And so the idea was, how to extend those networks. We went into the direction of adding more biological constraints. But I think the main ingredient that we introduced was learning. And so kind of what is interesting, and I think you were asking me about the similarities and differences between something like the HMAX model, which was a hierarchical model, very closely related to a convolutional neural network. But back then, I was educated with the belief that supervised learning and backpropagation through neural network was a no-go for biology, that there was...
That's still a no-go, as it is implemented in supervised learning current systems, correct?
That's correct. But I think people are more willing to consider the possibility that there are good enough approximation of backprop.
Yeah.
And, there's a flurry of papers that have come out in the past, 4 or 5 years, suggesting, with varying degrees of success, that there are plausible approximations of backprop. Back then, there was very strong tension between the field of biological vision and computer vision. An easy way to separate these two fields was by, the line was drawn at, supervised versus unsupervised learning. And so I literally spent a big chunk of my PhD thesis trying to come up with ways to introduce learning. The original HMAX didn't have any learning at all. The features were really kind of hard-coded. But I focused on unsupervised learning mechanisms, versions of Avian learning and other forms of unsupervised learning towards trying to learn kind of intermediate level visual representations, which did help. And so I think that was the difference between getting a network that would, I think it was easy starting with these paper clips, this wiry objects, black and white objects, to come up with a way to engineer neural selectivity for, bars and corners and combinations of orientations. But I think, clearly it was hard to come up with features that would just work for faces, right?
Yeah.
And the secret there was that as soon as we introduced learning, and even a very simple form of learning, but that would allow the network to figure out, good enough features to represent faces, then suddenly it started to work, and it worked, very well. And kind of what is interesting is that I remember very vividly, I think this must have been CVPR 2005. So CVPR is one of the major computer vision conference. I think we had posters with one of Yann Lequin, a graduate student, and we were literally next to one another, where we realized that, we were dealing with almost the same models, the same architectures. They were calling those convolutional neural networks. We were calling those feed-forward hierarchical models. They were using backprop. We were using unsupervised ABN type of learning mechanisms, meaning they would try to learn features that are discriminative between object classes. We were learning features that are frequent, right? That are occurring with high probability in some sense in whatever image database we were using. What I find interesting is that back then, I think, if I remember correctly, and maybe Yann will scream at me for saying that, but I think back then we were getting slightly better results than they were.
Oh boy!
And part of the reason is that the data sets were so much smaller. That we were dealing with data sets that had on the order of a few hundred classes of objects.
So you could really engineer to the features in a small data set.
Engineer also, supervised learning just wouldn't work. That backprop would just overfit massively to this training data sets with 100. And so, in a sense, unsupervised learning would do slightly better, not by a lot, but slightly better because, less overfitting.
Yeah,
essentially.
Very general. Yeah.
And so anyway.
So that's funny. So there's two posters right next to each other. This is burned in your memory now because it's kind of a classic case of, these two separate parallel fields moving along together. And did you, you couldn't peer into the future at that point, but did you feel like there was going to be definitive overlap or that it would still be separate?
The overlap did happen to some extent. So what is interesting is that if you look at the nitty-gritty details, I think the original kind of convolutional neural network would again, without getting into too much of the weeds, one of the key operations in those neural networks is the what we call the pooling operation. And that's the operation that allows these networks to learn invariant representations or invariant opposition. And back then they would use something more akin to an average operations. When the HMAX is called HMAX as in hierarchical max, the key kind of idea behind HMAX was that perhaps the right operation for building in invariance is a max, not an average operation.
And now CNNs do maxing, do max
and
pooling.
exactly, and this is as a result that I think the Yan started to play with the max operation, and that they found that it helps.
That's funny.
The other interesting thing was that again, to account for kind of divisive normalization and things like that are principles that have been long studied and understood in neuroscience. All our convolution included some kind of normalization operation, which again was not present in the original CNN. And I believe that there is a kind of systematic study from Yan's group done, maybe the year after or a couple of years later, where they systematically look at those, various ways of pooling and normalizing, etc. And they also confirmed there that the normalization actually ended up helping quite a bit. The modern version of that is, the so-called batch normalization, which is, one of the kind of key ingredients of the success of deep neural networks.
I mean, I know Jan's not shy about talking about the influences of neuroscience, back to the Hubel and Wiesel days and the neocognition and all of these influences. And then at some point, there's just so much interaction and overlap. It's just hard to parse out like when you were influenced. Did it come to you in a dream, or did you talk to someone at a poster, or how these things come about? So it's a pretty interesting and muddled history, probably.
That's correct. Yeah, I mean it's that's an interest. The overlap. I mean, what is interesting is that really it seems what I understand from Yan's comments is that Yan was influenced by Fukushima's neocognition, which was the kind of first real translation of Hubel and Wiesel's work from the 60s, early 60s, I should say mid 60s, into neural architecture. I think the same neurocognition motivated the HMAX. Then, the work that Yan and others were doing in the 90s and early 2000s was somewhat removed and disconnected from the work done by we discussed, the HMAX and Tommy Pojo's work, but, there's a zoo of similar models. Edmund Rawls did a lot of work in the years 2000. There was Dave Barrett, who did a lot of work done, in more kind of neuroscience, computational neuroscience groups. And, there was really literally no overlap and no discussions between the two fields. And then, I think, probably Yan and people like Jeff, I remember I wouldn't be able to come up with the exact date, but I remember, Jeff Hinton inviting me to give a talk at one of the CFAR meetings somewhere around this time. And I think this is the first time that as a grad student, I realized that, oh my God, there's so much overlap. It's kind of crazy to not having more fruitful kind of conversations. And
interesting. Those conversations are being had a lot these days, I suppose. I mean, that's what this podcast is all about, that essentially. So,
and of course, I think things have changed so much since then that the blur between computer vision and biological vision is almost non-existent, right? And just to make a small point, it's kind of I guess both sad to one extent, but also fascinating to realize that after having spent so many years of my PhD thesis trying to engineer a model that would, as closely as possible, approximate, the neural responses found along the ventral stream of the visual cortex, constraining, neurons in the HMAX so that, the neurons would exhibit similar, tuning properties like peak spatial frequency, receptive field sizes, and, you name it, going through decades of electrophysiology work.
Important stuff.
Constraint.
Yeah.
Right. And then realizing that, and this is the work that Jim DiCarlo has done, since, realizing that just taking kind of a state-of-the-art deep neural network that has literally no constraints in terms of receptive field sizes or tuning properties from biology, and seeing how so much better this neural network fit to experimental data compared to, perhaps simpler, older models that were, more grounded in neurophysiology. That to me was kind of, I don't know if I would call that a wake-up call, but certainly a major surprise.
So the pessimistic view would be, so when you look at one of those graphs that compares these modern convolutional neural net performance on like object recognition to the older classical models, HMAX is, it's always like the second best, third best, it's right up there. And HMAX performed much better than the earlier different models and a lot of its contemporaries. But so you could either look at that and think, oh man, we performed so poorly. Or you could look at that and think, man, we were almost there. So which is it?
Yeah.
Which do you feel? Both?
A little bit of both.
Yeah.
I mean, I think, yeah, a little bit of both. I mean, now we understand better what has been a key kind of engine of the gain in performance. And so, it's clear that backprop makes, we're having this discussion over supervised and supervised. And I was telling you that back in the CVPR 2005, we were using, learning of the convolutional layers. Visual representations would be unsupervised. People like Jan's group, and his group would focus on backprop. Back then, the data sets were too small for really being able to properly representation, so they would overfit. Unsupervised method would tend to outperform them. But of course, once the data sets became large enough, internet scale, with data sets like ImageNet, then, the gap started, there was not even any kind of possible comparisons between the unsupervised and the supervised method. So, to your point, yeah, I mean, if you look at, I would say it's both half full and half empty glass. Yes.
At the same time, you learned a lot about vision during that time, right? I mean, well, I'll ask you about that later because I want to know about, your advice to people who are getting into the field. So I'll ask you that in a little bit. I mean, one thing that HMAX and current deep learning nets have in common is that the vast majority of these models are working on object recognition. And it's as if we've just kind of made this assumption and accepted that object recognition is what our visual systems do. It's the most important thing. It's weird to me because whether it's a computer or a human, it's like we show them this picture of something. It's a static image and they can look at it. If it's a computer, you feed it in vector form, but it's just this image that's static. And that's not how we work. That's not how we turn our heads. We move forward and backward and the visual scene's always changing and everything. And I'm wondering if we've focused too much on object recognition as quote unquote the computation that vision does. What do you think?
Yeah, I completely agree. I mean, my interpretation of why there is so much focus on object recognition, I think it is two reasons. One is that it fits very nicely within the predominant framework in machine learning, which is the supervised learning framework. Again, we're talking about work in the 90s earlier. This is really the stuff that was formalized and understood relatively early on. So the idea of, organizing samples into categories, classes, natural object categories, become a very natural kind of testbed for those kinds of theories. So on the one hand, I would say this is the stuff that we understood and were able to formalize very early on. So that drove a lot of the early work. In addition, I think the value of such automated categorization systems for big companies like Facebook, Google, etc.,
sure,
helping you, make sense, of the deluge of images and videos we have to deal with on the internet, certainly help add focus to this kind of task and really try to solve them in full. Now, so I would say, this has been probably mostly an opportunistic take that scientists have followed. To your point, the relevance for biology is, I think you're absolutely right. We do not spend our days categorizing objects.
But it's interesting. I happened to be watching this interview or listening to this interview with Torsten Wiesel of Hubel and Wiesel, and he was recounting their early times recording these edge detectors and things like that. And he was saying, the dream is to understand how we perceive objects. And so it was even embedded in their early days of recording, like that is what we want to understand is how brains perceive objects. And so that notion has been also in biology, I suppose, from the beginning, if we consider Hubel and Wiesel the beginning, which many of us do.
Yeah, which is interesting. You're right. Yeah, I mean, you're right. Yes, that's yeah. And certainly, I would say to your point, I think this is a very poor proxy for, what the goal of a biological agent is, right? So our goal, cannot be just recognizing objects. We need to find food. We need to navigate a scene. We need to manipulate stuff. We need to mate. All of these tasks, I think, go way beyond what object recognition is. In addition, almost any way you want to count, there's no way we can get to the level of supervision, in terms of getting associations between individual images, retinal images or digital images, and class labels. And so clearly the way we learn is not through this, kind of presentation of random images in random order. And so, the level of supervision we're getting is by interaction with the environment. And so these interactions are a much better way to formalize and think about the goal of our visual system. So in a sense, figuring out how to manipulate an object is probably a much better proxy for the job that our visual system has to go through every day, as opposed to necessarily recognizing it.
Yeah. How
do we come about and recognize the object and come about to organize the set of our visual world into categories is, an important and interesting question, but maybe not the most important one for biological agents.
Well, you've mentioned also not to go back to HMAX and that distinction, but one of the things that modern deep learning networks do is not care so much about the biological constraints, but they perform a task. And that's the surprising thing, is like all you have to do is ask it to perform the task, not all you have to do. But by performing the task, all of a sudden the representations are similar to brains in many respects. So that's a very simplified way of saying it. So in that notion, the actual action of performing the task becomes important, primary almost.
You're right. And so I think what we've learned from that is that, purely unsupervised learning is probably not sufficient to account, at least in the ways that this has been formalized up to now, hasn't been sufficient to account as well as supervised training methods have. That said, it could also be that we haven't quite figured out the right learning approach. And so, I'm particularly excited about, some of the most recent developments in deep learning in the area of generative adversarial networks, and more broadly the notion of generative neural networks that are really just trained to synthesize images as opposed to categorizing them. And so I'm not aware of any kind of analysis so far that would have compared the ability of these networks that are not trained and optimized for object recognition, but rather have been trained to learn a generative model of natural images, natural statistics. And I wouldn't be surprised if we find very soon that this neural network even outperform the neural network that have been trained, supervised for, say, image categorization.
Yeah, it's coming, isn't it?
I'm sure. It's just a question of time.
Yeah. So, I mean, I have sort of gone back and forth on deep learning, my, opinion on it, right? So sometimes I think that it's a fundamental advancement. I mean, this is the cry of the masses right now, that it's going to change the way that we understand brains and intelligence, right? Other times I think that it's sort of like the latest in a long line of, fads that kind of coats neuroscience and puts a nice sheen on it, and we learn things from it, but it's fairly incremental is maybe the way that we'll look back on it in the future, at least in its current instantiation. So, but it's unclear to me what impact it's already had, right, in neuroscience. Has it fundamentally changed how we think about brain processing, or has it been incremental so far, you think?
That's a tough question. I think it has already changed the landscape in neuroscience, right? So, I think one thing that it has done already is that I think many of the tasks that we used to think as neuroscientists as really, really hard turns out to maybe not be so hard.
Yeah.
I think, if you look at the success of deep neural network for image categorization, right? So there are claims that are already for the, on ImageNet, categorization of 1,000 natural object categories. There are claims that, the state of the art is already outperforming humans, right? Face recognition, there was a paper published a couple of years ago by Jonathan Phillips, who has been working for the government, for decades now, assessing progress in facial recognition. The claim of this paper is that, they made a systematic comparison between the accuracy of deep networks versus not just naive facial recognizers like you and I, but the very best facial recognizers we have, who are these facial forensic experts.
I didn't even know that these people existed, first of all.
Right. But they're on par. If anything, the deep neural network is actually a fraction of a percent of accuracy higher than those guys.
Okay.
That to me is mesmerizing. And if you had asked me the question, back in 2005, we were talking about the CVPR 2005, just a little while ago. I would have never expected to see that kind of improvements. I don't want to say within my lifetime, but certainly within the next 10 years. So that to me is fascinating. I think this is potentially changing, at least my view of what is easy and hard in vision. So tasks that I thought would be really, really hard, like natural image categorization, because these are natural images and they are hard to parameterize, or facial recognition, turned out to maybe be easier tasks than I thought.
Yeah.
And yet, what's also fascinating is that there are so many other tasks that do not seem quite as hard, and that turn out to be much harder than we expected for these deep neural networks.
Yeah.
Few examples, but if you look at adversarial images, for instance, that are pretty well known, but just briefly, the idea is that it's possible through optimization methods to come up with a very specific pattern of targeted noise that could be superimposed on images so that a neural network would be tricked, or what we call fooled, right? So the idea is that I can take an image that a particular neural network is very confident at recognizing as, say, as a cat. Researchers have shown that it's possible to engineer a very, very small amount of a pattern of noise that gets superimposed on the image that will fool the network in classifying this cat image in, any arbitrary class of object. And what's interesting is not so much that you can do it, because mathematically this could be shown, but what is interesting is that how little amount of noise is needed to get this neural network that achieves superhuman accuracy on normal images, how this network can so easily get fooled by a tiny amount of noise.
Whereas when a human will look at the noise,
where the human doesn't even, and the human barely sees the noise, if at all.
I can't generally.
Right. So that to me is fascinating. Reconciling, the ability of this neural network to exhibit superhuman level of accuracy on the one hand, and then fail miserably in with a tiny amount of noise.
Yeah.
Similarly, I think there's a growing consensus that it turns out that maybe there is not so much evidence that deep neural networks generalize much beyond the training data that was used to train them. So if you had asked me 10 years ago, something like ImageNet, 1.5 million images sampled from the internet, that should be a gold standard. Like if this is random images collected on the internet, that should really tap into, the core problem of object recognition. Well, it turns out people are realizing that, ImageNet is highly biased, that, a lot of the images are taken by human photographers. And so, as typically we tend to center objects, we tend to take objects under certain canonical viewpoints, under backgrounds that are consistent, with the class of objects.
And we love cats.
We love cats. You get a lot of cats in your house on your sofa as opposed to, the middle of the street. And so there turns out to be all these kind of easy tricks that neural network could in principle leverage that a human subjects might not actually be able to leverage because we don't have the ability to sift through millions and millions of images. But computers have this ability. And so it is possible, although I have to be cautious, of course, about how strong of a claim I'm making, but it is possible that those neural networks leverage a lot of tricks that are present in those data sets. I think there are two examples that are speaking to this. Very recent work done by Boris Katz at MIT has been to try to re-engineer a novel ImageNet. And so what they did is that they asked people on the internet to take pictures of objects from certain categories, categories that are overlapping with categories of ImageNet. But they essentially ask people to take pictures of those objects. They could ask you to go into your kitchen and take pictures of forks, right? But they would ask you to take pictures of forks under very constrained kind of viewpoints. So you'd be asked to take a top view, a side view, and then to take pictures of those at different maybe distances, maybe under background that are consistent or inconsistent. So they have complete control over the range of transformations that are being applied to those objects, right? So forcing truly the need for a truly invariant representation, invariance to position, scale.
But you're still in the kitchen. Are they saying hold up the fork with the road in the background or something
They
too?
did both, or they would ask you maybe to take the fork on your sofa, for instance, out of context.
Yeah.
So those are still conditions that are trivial for human subjects, right? You'll still recognize the fork, etc. What they've shown is that if you take deep neural networks that were trained on ImageNet, there's a massive drop in accuracy when you test them on this novel data set called ObjectNet. Okay, and so what is even more interesting is that they've also shown that it's not just a kind of what we would call a low-level transfer problem, because even if you, I'll get a little jargony and I apologize for that, if you try to fine-tune this neural network, so you try to retrain them a little bit on this new data set to make sure that they adjust to maybe the different illumination, the different level of pixel intensities, etc., they do not improve. Okay, and so the conclusion is that those neural network potentially haven't learned to solve what most people would qualify to be the core object recognition problem, where you would have to recognize objects under any viewpoint, any background, etc. That they are really kind of overtrained and perhaps overfitting to ImageNet, which contains only a very small subset of all the transformations and image degradations that can be applied to natural object categories. So that's another example, I think, suggesting that perhaps we're not quite as far as we think we are in terms of achieving human-level object recognition. I think this is exemplified if you look at the trouble that people are having with self-driving cars, right? So essentially, right now we have many startups. Many companies driving, having cars driving millions of miles per year with a human behind the wheels, right? The human, the car driving itself, except, when the car, either makes a mistake or seems to be confused where the human has to take over the wheel. What is interesting is that we find that in general, those cars can go on and on and on and on for, up to, I was told, even on the order of 100,000 miles with that human interaction. The idea is that, those companies are potentially, this once in a while that the humans is taking control over, this could be a failure of potentially the recognition system of the car, that a pedestrian was not detected, or that, a flying plastic bag was wrongly detected as a pedestrian's. And it's pretty clear that those companies are essentially trying to harvest, kind of those edge cases of vision, right? The pedestrians in this weird illumination, the weather condition that was not used during training, etc.
Yeah.
But what we're also seeing is that this is taking a long time. It's not just millions of miles, but there are always those edge cases, right? So you can drive as much as you want. There will always be cases in vision that you've never experienced, right? Never seen a particular sun in this particular position, particular weather pattern, and particular pedestrians wearing this particular shirt. And so what we're seeing is, in a sense, I think the limit of this, the current deep neural network approach, where, the level of generalization goes just, maybe beyond the training data. And we're still missing this, level of abstraction that, is so representative of human vision, where, at some point you don't need to continue seeing any more pedestrians crossing the road. We just get it. And that, I think, is the key ingredient that is missing.
I mean, I recently had Uri Hasson on the podcast, and he's had this transition in his approach to thinking about neural networks and how brains compute things. And he has come to the conclusion that, okay, we have these neural networks, and they overfit things if we let them, right? Just like you're talking about. And if you have like a really small data set, you're way over parameterized, and you have these big networks, and it'll totally overfit it. And he's come to the conclusion that this is how brains work too, but because when you give a network all of these that's over parameterized, let's say all these forks, in different vantage points, that is still, so you probably wouldn't have a fork by the moon at that point, right? And so that could be like an outside kind of example still, because you're not gonna give it every single example possible. And so that the network and our brains will still, won't generalize necessarily, will fit statistically to the minutia as much as possible, every single different condition. You've talked about these networks, that you can show, like, you just memorize all the data instead of generalizing, right? And because we're exposed to so much data, our brains, and by the way, our brains are massively overparameterized, is one of his points as well, more overparameterized than any current deep network, right? And that's what our brains are doing, but that is good enough because they're so powerful to essentially almost everything is within our training set. So that then when we're going to be tested on it, it's basically within that what's called the interpolation zone, and that our brains are bad at generalization or extrapolation, an example that's outside being, the training set essentially. I don't know. So this notion it kind of, got me on board essentially that, okay, we're not so general and special. We're actually overfitting everything. He calls it direct fit. And that, his argument is that this is the way evolution works over massively longer timescales, that, evolution works by directly fitting our biological fitness or whatever to the environment. And that's not all brains do necessarily, but that's, he puts it between like 70 and 90% of what brains do. And I don't know, what do you think of this notion?
I mean, I do think, I agree with many of the things that I've heard. I do think that there is a qualitatively different level of abstraction that's possible in this, again, as a current iteration of deep neural network and biological homologs. Mm-hmm. One example, learning something as simple as the notion of sameness from training examples. Right. So I can show you, pairs of shapes or multiple shapes. I give you maybe a handful of images, and I don't tell you the rule, but I tell you those are positive examples, and all these positive examples would contain pairs of shapes that are always identical, maybe up to a transformation to be determined. And then the negative set shows pairs of different shapes or colors. I think depending on the task, you could imagine cases where human subjects could learn that from maybe 2, 3, 4 training examples, right? Right. We and others have shown that in the same condition, it takes, orders. I mean, I'm talking about tens of thousands of training examples for neural network to learn those tasks. And that even when they seem to learn the task, they do not seem to necessarily demonstrate an abstract understanding of the rule, which would be figuring out whether two things are the same or different, because they never generalize much beyond the shapes that are used for training.
Are these feed-forward networks? Or are they
convolutional neural network? We've also tested, kind of what a few years ago was considered the state of the art in visual reasoning. Those are called relational network. Yeah. And what's fascinating is that people have done the experiment on newborn ducklings. You can take a pair of a very simple geometric shapes, cubes and balls and of colors. You take a pair of this, you wiggle them in front of a newborn duckling, you perform what is called imprinting, right? Yeah. Which normally appears at birth when the duckling imprints on their mothers. A single training example, and yet those authors have been able to show that the duckling do seem to generalize beyond the appearance of the shapes used during training, right? So they can generalize to different colors, different shapes. From a single training examples, they seem to get this notion of same or different. And that is at the level where, I would challenge anyone to provide a neural network today that can learn the notion of sameness from a single training example. Yeah. And I think this is the level of abstraction we're talking about. Seeing a pair of blue cubes, and from that understanding that the rule is same or different, and being able to generalize to other colors and shapes, etc.
Yeah. On the whole, because we have a lot more to get to, I suppose. So on the whole, you don't think deep learning is overhyped then?
I think there's a little bit of both. I think the success we are seeing is tremendous.
Let me restate, actually. So with respect to neuroscience, you don't think deep learning is overhyped with respect to its potential in neuroscience?
I think it has already demonstrated the benefit for neuroscience. We went through this example where, I think it has allowed us to rethink what's easy and hard in vision. Yeah. Right? So we just went through examples of, image categorization, face recognition that turns out to be easier than we thought. And yet simple tasks like figuring out whether things are same or different, or very basic visual tasks very simple shapes, colors, parameters, that would seem trivial for a computer vision algorithm turn out to be much harder than we would have imagined for neural network. And so I think it's kind of what deep neural network has already done is allowing us to rethink a little bit the framework of visual tasks, the space of visual tasks. There's a ton of work, obviously, on using deep networks in vision. I mean, I think we alluded to the work of Jim DiCarlo, feeding deep networks to neural recordings done along the ventral stream of the visual cortex in area V1, V4, IT. There's amazing work done by Serre and colleagues at Stanford, where they've been feeding those convolutional neural network to retinal data. And then if you look at the quality, the goodness of the fit, I mean, we're really talking about goodness of fit that is very significantly better. So massive improvement in our ability to capture something about the response of neurons along visual areas. That I think is very significant, right? That's showing us that there is much more explainable variance that can be captured from neural recordings, from the response of neurons that is observed. I think the part where maybe it's overhyped is that I think there is a lot of work that is, by lack of a better and more politically correct way to say it, is mindless. I think just feeding arbitrary neural network to arbitrary neural data is not going to get us very far. Mm-hmm. But I think we're at the point where the field is understanding that we have neural network that can capture a lot of information and the variance observed in neural data. The next step will be to try to open up the black box and figure out what it is in those neural networks that enables them to go beyond some of the older models that we went through. And so I think if we do this, there's the opportunity for deep neural networks to do what computational neuroscience hasn't been able to do until now, which is really to set the ground for, making predictions, testable predictions for neuroscience that can be tested. And so I think the next phase for this line of work will be to have essentially closed loop experiments where, based on the initial recordings we have and feeding of data permissible with the current architectures, people will be able to make specific predictions about how specific maybe class of interneurons or very specific type of neurons would contribute to very specific kinds of computations that can then be interrogated with kind of modern neuroscience tools such as various kinds of imaging, various kinds of optogenetic techniques and things of that sort. So I do not think this is overhyped. I think there is potentially room for improving the kind of work that's being done, but I'm certainly one of the more optimistic in thinking that this is just the beginning, and this is opening up doors that I haven't seen open until now.
You're doing a lot of the work on implementing biological constraints still, things like excitation and inhibition, and I hope that we get to a lot of your work actually here. But, one thought is, well, do we need neuroscience at all? Do we need to study brains, or can we just bypass brains, keep building new networks and throwing more computational power at them and asking them to perform tasks, and we could get to whatever, artificial general intelligence, or eventually build quote unquote intelligence. And I don't know that we're ever going to come to a satisfying notion of what intelligence is. So that is a question in itself. But, do you think that do we need brains? Do we need neuroscientists?
Well, I think I think it depends on your goal. My goal is to understand the brain, so I see deep learning as a tool towards achieving this goal. So there is no question that by testing the possibilities and limitations of current computer vision deep neural networks, that gives us a lot of information about what can and cannot be done with a finite set of what I would call neural computations, right? Mm-hmm. So that certainly gives me a lot of information, useful information for brains, which in turn allow us to ask the question, what are the additional computations that brains are able to implement that are not currently present in modern deep neural networks that potentially could help a deep neural network. And so I think this interplay between computer vision, assessing the limitations, strengths and limitations of computer vision, allows us in turn to understand, what makes brains so special. And so in that sense, I think, given some of the limitations of deep neural network that, we've alluded to, and in the short term, there's certainly, and given that those are tasks that are, much easier for biology, there's certainly a lot of room for neuroscience to contribute to deep learning. And if we have time, I hope we can go through some more specific examples. Now, to your point, that's not to say that the ultimate solution to achieving true general intelligence will require biology. After all, these are brains and computers are very different kinds of strengths and weaknesses, very different kinds of power requirements, etc. And I wouldn't bet my career on the fact that down the line the solutions or the optimal solution to general intelligence has much to do with neuroscience.
Let's play a fun game real quick. So I thought of this little thought experiment. So we have a number line from 0 to 100, and 0 is the McCulloch-Pitts artificial neuron, and 100 is, I don't know, true intelligence, human-like intelligence, something like that. Where on the scale is current deep learning?
Oh, that's on the current scale, I would say it's probably at about, a scale of 20, 20 would be my guess.
20. All right. I'm going to keep asking people this, and we'll get a collection.
Yeah, that's a great question. Yeah, you can get statistics. And
yeah, I need data, right? It'll be a small data set, so I'll overfit, but oh well, And that's funny because I think yours is kind of pessimistic. 20 is somewhat pessimistic, but we'll see.
Sorry, so maybe let me restate that. I guess my answer was if I go from the McCulloch and Pitt model of a neuron all the way to a model that would capture every possible biophysical phenomena of a neuron, we're at a scale of 20. Now, maybe I misunderstood your question.
Yeah, let's reformulate the question.
Which had more to do with how far you need to get towards biological realism to achieve, general intelligence. It's not clear to me that we need to pass 50 anyway, right? That, I think this is very much the point that Yann LeCun has been making for, many years now, that, it could well be that, coarsely approximating the main two kinds of functional cells found in the visual cortex, simple and complex cells, which, are well approximated by convolutions and kind of putting operations. Maybe that's all you need, and with the proper, learning algorithm, that's all you need to get, past human visual intelligence. And so, so I don't know if I'm fully answering your question.
No, it wasn't a well-formed question. See, because what I kind of wanted to go is from McCulloch-Pitts, to the birth of this AI neuroscience collaboration, right? To whatever we would consider satisfying the general intelligence, right? And where we are in that march, not necessarily like how much biology we need to implement, how specific the models need to get, how biologically real, just like where deep learning, because there's so much hype about deep learning right now, and everyone thinks, we just need to put two of these networks together and we're going to have an intelligent system, but my feeling is we're way far from that. And I wonder how far, so that's what, where in the current state of deep learning on that number line are we,
Yeah, I mean, I'm not trying to avoid the question, but the difficulty in answering this is that it depends what the actual final metric will be. So one example is that if you look at self-driving cars, I mean, I think if you look at it by, the level of human intervention that's actually happening, you could claim that we're 99.9% there, right? I think those self-driving vehicles have a false alarm every, hundreds of thousands of miles, right?
Yeah.
Now, the problem is that if your goal is to have, no mistake, then, I don't think the current paradigm of, looking for mistakes of the system to reinject those mistakes in the training data set is going to get us to that level. And so on the one hand, you could say we're 99.9% there, but if your goal is to achieve 99.99999% accuracy, then I think we're not even halfway there, because what we're going to need is much more than more of the same.
Yeah. Well, it needs to be a logarithmic scale too, I realize. And it's tempting to say, okay, well, Turing test, that's the end, but that's not a good test to me. So yeah. Okay. I'll have to reformulate the question. So thanks for sharpening my questions here over the long haul. Well, Thomas, you've made models of cortical columns in vision, and they have pretty specific computations about how classical receptive fields and extra receptive fields interact with excitatory and inhibitory connections, and it's quite complex, and it works really well, as you can tell us more about. But there's this notion of the canonical microcircuit in the cortex, which is sort of repeated across cortex. And if cortex writ large is just this repeated computation over and over and over. The same basic computation happens over and over. So what do you think? First of all, do you think that that's true? And if so, what do you think that the cortical column computes? What's that general computation?
Yeah, so I think there's little to dispute that claim, right? So I think the evidence is there, and there is plenty of evidence for cortical columns potentially being the building block of computation. And so chances are the basic computational unit in biological neural network not being the neuron, but maybe something more akin to the cortical column. So I think that it's easy to believe. Again, I think that there's pressure from in biology for things to be more easily, to be sharpened by, to be set by genetic. And so I think a lot of that repetition and the fact that we find these motifs, etc., is probably a byproduct of the need for much of the wiring to be genetically encoded, right? Because we need to have certain minimal functions at birth.
Imprinting.
So imprinting would be one of them. If you're a duckling, there's evidence now that babies learn face recognition in the womb, right? So there is already a lot happening. And so I think, genetic is probably one of the, that potentially, the existence of these motifs is probably a byproduct of a lot of genetic. Now, what I think is, your question had to do with, actually, do you mind reformulating your question?
Yeah, well, so, I mean, there are been a lot of suggestions of what the cortical column computes, right? It's computing a prediction. LSTMs have been used as a model, to try to model the cortical microcircuit and its computation. Maybe it has some sort of gating function, right? Like an LSTM that it's all built in. It's just a repeating motif of LSTMs, the cortex. And you have this, beautiful model of that captures a lot of the receptive field dynamics and a lot of visual illusions. And I'll point to that work in the show notes. And if it would help, you can describe that modeling, because what you're essentially doing is modeling the canonical microcircuit.
Yeah, so that's a good point. So if you look at what a modern convolutional neural network does, a feed-forward neural network, much of the wiring is happening from a particular layer of processing onto a higher level of processing, right? So so in a way, the only way for neurons to communicate is through bottom-up processes, or what we call feed-forward processes. Yeah. Now, in contrast, if you look at the visual cortex, there's actually extensive cortical feedback. So this feedback takes two forms. One is what people commonly refer to as lateral or horizontal connections. So those essentially link neurons and cortical columns within a layer of processing. And as a maybe point of clarification, especially in early visual areas, columns correspond to typically a group of neurons spanning potentially a range of selectivity. So in the primary visual cortex, you'll find at least a hypercolumn will contain all neurons tuned to all possible orientations and maybe a range of spatial frequencies, etc. But one commonality between all these neurons within these cortical hypercolumns is that their receptive fields overlap, right? So they're all responsive for the same part of the visual field. Yeah. Okay, so if you add horizontal connections or an ability for neurons to communicate laterally, that means that essentially you allow neurons that have receptive fields centered at different locations to communicate between themselves. So essentially you allow the information not just to flow upward, but also laterally across region of the visual field.
Which is, you're saying, one fundamental type of recurrence. The other type being the top-down.
The other type being the top-down, going from a higher level layer of processing onto a lower level of processing. So some of the early work we had done, and I think this is the work that you were alluding to, was really trying to figure out a way to go beyond this very simple model of neural responses as found in current convolutional neural network. As I mentioned earlier, these neurons can only propagate information from the bottom to the top. And so essentially, when you go into different layers of the hierarchy, you'll find that neurons have what we refer to as a receptive field, which is a part of the visual field that can trigger, elicit a response from them.
Yeah.
What is interesting in neurobiology is that you find that neurons don't just have a classical receptive field, but they also have a zone, an area right outside, sitting right outside of their classical receptive field that can modulate their response. So by construction, by definition, the extraclassical receptive field, if you stimulate that part alone, will not elicit any response from the neuron. But if you stimulate the classical receptive field, then what you put in the extraclassical receptive field can have a tremendous impact on the neural response. Those kind of effects are completely inconsistent and hard to reconcile with, modern kind of convolutional neural network. So we wanted to understand that and build a model of biology that would allow us to explain those, type of phenomena. And so we started with a very simple model of horizontal connections. We looked at the anatomical and neurophysiological data available to try to figure out how we need to link neuron both within a cortical hypercolumn, but also across cortical hypercolumns, so that we could explain the neurophysiology of this so-called extraclassical receptive field phenomena. Mm-hmm. We were able to do this, and that was our starting point. The next step was to show that we could leverage this model of neurobiology and test how far we could go in explaining so-called visual contextual illusions. So there are many of those, and they are hard to actually explain, without visuals. But one example would be color perception. So your perception of color, what we refer to as the reflectance properties of a surface, are highly context dependent. So I can show you a little gray patch of a colored gray patch. And so if I force you to see through an aperture and there is no context, you'll be very good at recovering and the exact shade of gray that's being used. If I start embedding this gray patch into very context of different color, your perception of this gray patch will be altered completely. And this is of course very well known. You know that painters are know these facts very well, and they will never choose a particular color in isolation, but they will always choose this color next to other colors. And so those are called color contrast effects. If I embed a gray patch on a red background, the gray patch will look greenish. Conversely, if I show you this gray patch on a green background, the patch will look reddish. And there are many such phenomena spanning, many visual modalities. For instance, I can show you bars at different orientations. Your perception of the orientation of a center bar can be drastically affected by what I put in the surround and the orientation of the surround. Same with motion. I can show you moving stuff, and if I embed this moving stuff into a background of things that's moving in different directions, depending on the kinds of movement of the background, you're going to see things moving in one way or another. Mm-hmm. So our perception in a way is to a large extent context dependent. Your perception of your particular perception can be drastically affected by what is presented in the context of a particular stimulus. So we wanted to test the ability of this very simple model to account for those, and we found that, to our surprise, we were able to account in relatively good detail for many of those contextual illusions, and we produced very known psychophysics results. Now, the skeptic could say, well, I'm a computer vision scientist. Why should I bother? Essentially, you're telling me you've been able to design a circuit derived from neurophysiology that is essentially able to get fooled by the context, right? Because that's what we do.
Right.
Illusions are deviation of our percept from the physical reality of those stimuli. But we suspected that a lot of these visual illusions are kind of just edge cases, that they are not really bug of our visual system. They're edge cases in the sense that they are very artificial. They are very different from the kinds of visual stimuli that we have to deal with on a day-by-day basis. And so we thought that, a system that exhibits this sensitivity to contextual illusions would demonstrate many other benefits in maybe more realistic kind of natural recognition types of problems. And so we wanted to demonstrate the benefit of this kind of highly recurrent neural network, where once again, the flow of information is not just bottom up, but that neurons with receptive fields spanning different regions of space are able to communicate horizontally to solve jointly certain kinds of tasks. And so the first task we came up with is a task that was motivated by earlier work in cognitive psychology, and we call that the pathfinder. So the pathfinder is very simple. I give you images. I don't tell you the rule. You have to learn that from examples. The positive examples include both positive and negative examples include markers, 2 markers. The positive examples, you'd find that there is essentially a path, a contour that goes from point A to point B.
Like footsteps in sand or something, right? Like different.
Imagine in sand. In practice, we use very simple tasks, simple stimuli such as, black and white pixels and things of that sort. But yeah, or imagine following footsteps in the snow, right? Where you would have multiple footsteps, and I tell you, you're at point A. Is there a way following either a footstep that would take you to point B?
Yeah. Okay.
And the negative examples would, the 2 markers would fall on different, path or contours. We thought that the way for a feed-forward neural network to solve this task, we thought that the feed-forward neural network would have to reach or build receptive fields that at least encompass both markers and the entire path linking the 2 markers, right? And in order to figure out the task. And so the way modern deep neural network grow their receptive fields is through depths. Okay, and so the prediction was that if we parameterize the stimuli so that we test neural network with increasingly long contours or path, the prediction was that the minimal neural network, the depths of the minimal neural network that would be able to solve that task should grow.
Should grow, yeah. As the path grows, it should grow.
As the length of the path grows.
Yeah.
And so we verified that and confirmed that even for a very simple task, black and white images, even million of training examples available, again, for a task that would take human subjects, potentially just 1 positive and 1 negative examples. Feed-forward neural network can solve that, but in the extreme case, we had to reach hundreds of layers of depth to solve this, what is otherwise a very trivial task,
right.
and hundreds of thousands of training examples. In comparison, we showed that if you take one of our basic circuits, highly recurrent, circuit that leverage recurrent connections across locations, across cortical columns, then we find that the single layer can solve the task invariant to the length of the path. So it can solve that with a single layer, with orders of magnitude less free parameters. We're talking about over-parameterization of modern deep network just a few minutes ago.
Yeah.
3 orders of magnitude less free parameters, and a fraction of the number of training examples needed. Okay, so this is one example, this kind of what I would refer to as incremental grouping task where you have to literally follow a path from point A to point B, are very natural for this kind of recurrent neural network. Feed-forward neural network are what we call universal approximators. So in the limit of enough units and enough training examples, they can learn any arbitrary task, but they will do it in what I would call the brute force way. It was going to take them a lot of training example and a lot of neurons to do what is otherwise trivial for a single layer of processing with the proper kind of recurrent feedback.
So, I mean, modern convolutional neural networks have grown, and I don't know what the latest number of layers on average being used is, 200, 300?
Well, it depends on how you count, but yes.
Sure.
So because now some of these neural network are actually what we call ensembles of neural network with 100. You could say this is equivalent to thousands of layers of processing.
And so what you found with this and what you claim in general is that recurrence is a way of replacing that depth with fewer parameters.
Absolutely. So what is interesting is that there is a task that has been extensively studied, which is called the rapid image categorization. The idea is to flash images very briefly in front of human subjects, force their response to be as fast as they can. And the assumption is that when you constrain the visual system to operate at its temporal limits, what you're doing is that forcing the visual system to operate in what we refer to as a single feed-forward sweep of activity. So although there is massive feedback in your visual system, the assumption is that when you press for time, if you have to detect a tiger, and move away from a predator, your visual system can do that in an almost automatic reflex-like way through a single feed-forward sweep of activity with limited contribution of the feedback. The motivation for feed-forward neural network was originally to try to account for these kinds of rapid visual processing, right? And we were talking about HMAX. That was one of the goals, to ground one of those network in electrophysiology and to demonstrate or to at least assess the consistency or inconsistency of responses from such a network with those of human subjects. Now, what is interesting is that the HMAX had, on the order of maybe, I think there was 8 layers of processing. Mm-hmm. Depending on how you count in human subjects, people would say probably anywhere from, the human subjects has anywhere between 6 and 12 layers of processing during this feed-forward sweep of activity or rapid categorization task. So arguably, your feed-forward visual system has potentially anywhere from 2 to 3 orders of magnitude less layers of processing than the state-of-the-art in deep learning. What is interesting is that the HMAX was consistent with human subjects during, because people do make mistakes if you force them to respond fast. The HMAX was able to show that it was consistent with human decisions. So in other words, it was making similar pattern of errors.
With the rapid categorization task.
With the rapid categorization. So the point that I'm about to make is that today, those very deep neural networks outperform human subjects, not just in rapid categorization tasks, but even when in unconstrained visual recognition tasks. I can show you pictures of, different kinds of boats and insects. Those deep neural networks will be doing much better than you, even if I don't give you, any limitation in time. And not just because you don't know the name, but because really, you're almost at the limit of what your, the level of detail that your visual system is able to categorize. And so, to some extent, we've engineered feed-forward neural network that are orders of magnitude deeper than our own visual system. They outperform what our visual system can achieve in a feed-forward sweep of activity. And so in a sense, they've gone beyond, they have diverged from essentially the way our visual system actually works. As you pointed out, my main argument, and that of many others, is that the way by which we can increase our depth of processing as human subjects when we're allowed more time, right? So if I give you a 500 milliseconds to perform a task, you'll make some mistake. If I give you an extra 200 milliseconds, you'll start doing less mistakes. Mm-hmm. So the argument is that the more time you have, the more you see and the better you get, right? The way this is done is not through static processing depth in your visual system, but by allowing feedback to essentially kick in and potentially refine some initial decision that would have been possible through an initial kind of feed-forward sweep of activity.
So do you think, and I want to talk a bit more about the recurrence aspect of this, but so if we built a convolutional neural network that was 10,000 layers deep, would it be, is there something that it would be missing in terms of what recurrence would buy us, So you just talked about the ability of these lateral, horizontal sort of recurrent feedback projections. And you were just talking about recurrence as a way to be able to spend a little more time processing an image, for instance. So what are some other things that recurrence might be able to buy besides just computational efficiency? Because you don't want to build the biggest convolutional neural network if you can build a smaller recurrent neural network. So that's fine, but let's take efficiency off the table. But biological, skill-wise, right? What can recurrence buy us?
Right. So just to get this out of the way, as we said, feed-forward neural network are universal approximators. So if you give them enough units and enough training samples, in theory, there is no task that recurrent neural networks can solve that they cannot solve.
That's right. So we could make a near infinite one hidden layer network, and it could do, in theory as well as a very deep network.
And vice versa, right?
Yep.
So that, right. Now, there's a number of things, so the interesting question becomes, what can I learn with as small as possible number of samples? And so what you find there is that potentially if you try to, if you try to leverage recurrence, you can increase processing depth through time without necessarily increasing the number of free parameters. So what I mean by that is that, and there's a lot of debate and a lot of work being done today in this field to try to formalize this a bit better. The kind of textbook machine learning or golden rule of machine learning is that if you want to generalize well, you need to force some constraint on the number of parameters in your network or the degrees of freedom of your parameters. Mm. And so to a first approximation, you want to be in regimes where you have more samples than free parameters. With deep neural networks where the other way around. ImageNet has 1.5 million training examples. That seems like a lot, but the state of the art has hundreds of millions of free parameters. And yet, they seem to be working to some extent. So that's kind of a puzzle. But certainly, in general, controlling the capacity or the number of free parameters or the degrees of freedom of a learner is never a bad thing. What a recurrent neural network allows you to do is to some extent recycle the same computation over and over again. And so essentially increase the processing depth through time while controlling, because those recurrent connections are fixed, they do not contribute to increasing the number of free parameters or degrees of freedom. So in a way, a recurrent neural network might be able to do as well as a much, much, much deeper neural network with many more degrees of freedom, many more free parameters. And so that means that it has an advantage that it might be able to learn much faster from far fewer training examples. And so in fact, one of our paper that's going to come out at the next ICLR conference is showing precisely that if we leverage those recurrent circuits in the context of image segmentation and contour detection, as a side note, the state of the art are still very deep feed-forward neural network, and they do achieve human level of accuracy at deciding whether there's a contour or an edge at that particular image location. So there's not much room for improvement. But the problem is that to get to that level, you have to go through a lot of hoops. You have to, do some pre-training on ImageNet. You have to continue fine-tuning on Pascal, and then you have to continue, fine-tune on the actual data set. So there's so much training that goes on. But yet,
works.
Yeah. I have to confess that this is human level of accuracy, so this is quite impressive. What we've shown is that if we just leverage the recurrent neural circuits that we've just been discussing, we can also achieve human level of accuracy when we use all the bells and whistles and all the engineering that comes along with training those networks. But once we start kind of reducing the number of training examples available to the system to learn, then we start seeing a very kind of drastic improvement in the generalization ability of the recurrent neural network. We find that, for instance, we can achieve the same level of accuracy as a very deep state-of-the-art feed-forward neural network. So we can achieve the same accuracy as the system using 100% of the training set with only 1/10 of the training sets. So, it's a very substantial improvement in the efficiency or how many training examples those neural network need in order to learn any particular task. Now, to be honest, this is contour detection. And there are many reasons to suspect that contour detection is kind of an optimal task to leverage this kind of horizontal or feedback connections. I think the jury is still out as to which, if any at all, other visual recognition tasks will similarly benefit from the inclusion of feedback mechanisms. So right now I have students working on the problem of color constancy, recovering the color or what we call the reflectance property of a particular surface in a way which is invariant to the color of the light source. Again, we suspect that the feedback will help us tremendously there, but I think the jury is still out, and this is still very much an ongoing project.
The work you're describing with the pathfinding work, I think that's what you called it. Is that a visual reasoning task? Does that fall under the?
We call it visual reasoning because I think this is certainly the kind of task that you might not be able to solve in this kind of rapid image categorization mode. So presumably this is the kind of task that require additional computation. We call it visual reasoning, but I think we can.
But yeah, I mean the reason why I ask is because you do work on things like that, and I'm wondering what other domains recurrence might be important for in our cognitive abilities. Right? You've mentioned I think attention and search task, things like that, and I don't know if you want to wax poetic about those. What other abilities recurrence might be good for.
So for instance, we were earlier on we were talking about the duckling and those same different tasks, right? So there is evidence that human subjects solve those tasks with the involvement of attention and working memory mechanisms. Both of those functions require feedback. And so, that could be an additional kind of role for feedback that might be needed to solve, what I would refer to as visual reasoning tasks beyond just, simply image categorization. Another possible role of the feedback, which is something that, we had found already many years ago with the HMAX, is that feed-forward neural network tend to have a hard time dealing with clutter. So they can do very, very well when there's a single kind of well-isolated object. But the more you embed this object in clutter, the harder it gets.
Don't take it into my children's room, in other words.
Oh, I see. Yes. And so I've been speculating that to deal with clutter, our visual system leverages attentional mechanisms. So essentially an ability to somewhat zoom in onto a region of interest and then essentially focus processing on that region of interest. Essentially, in a way, suppressing, forcing the visual information to be only from that part of the visual field to be routed to higher visual areas. Essentially, explicitly suppressing clutter. A few years ago, we had a collaboration between the Poggio Lab and the Decimon Lab at MIT when I was a postdoc there that has shown precisely that if you do monkey electrophysiology in the inferotemporal cortex, and you try to decode the identity of an object shown to a monkey from a small population of, say 100 neurons. If there is a single object, you can do that, perfectly from a small population of neurons. If you start putting multiple objects in the receptive field of neurons, then the accuracy drop, right? So essentially the neuron is sensitive to clutter just the same way as the HMAX was. But then if you train the monkey to attend to one particular object location, say at a location corresponding to one of the objects presented in the receptive field, then suddenly the same neural decoder that was trained on the presence of a single object in the receptive field, then start working again, and then you can start decoding what's going on at the cued location. And so what that suggests is that this is essentially what attention does. Attention has a way to somewhat suppress the clutter and force receptive fields and processing more generally to be focusing on an object of interest. To be clear, those kinds of attentional mechanisms are known to rely on feedback mechanisms.
That account of attention conforms with how we understand human attention mechanisms in action anyway. So that's great. So I mean, we could go on and on about feedback, and recurrence has become really popular in the AI world as well. And obviously, brains are massively recurrent. So this is an extremely important thing to build into our models if we want to really understand how brains are processing information. Another obvious thing that brains do is create spikes, action potentials. And I know you've done work on sort of getting around that, essentially. So you've modeled spiking-like features by using complex numbers. And we don't need to go into that work. I mean, people can look it up, and I'll point to it. But basically, you've avoided modeling spikes by going around it by using these complex numbers. And like I just said, recurrence has enjoyed this rise in deep learning. And recurrence has always been there since the very beginning, but it's sort of become more popular recently. Do you think spiking is going to enjoy a rise at any point, or are we going to use complex numbers always to avoid it at all costs?
Yeah, so that's a tricky question. I have to be careful to answer because I have a lot of friends working on spikes and spiking neural networks.
You call them friends?
My view is that so I think spikes potentially serve a clear role in biology. There is an efficiency, right? A kind of role. I know that there is, for instance, exciting work happening right now in hardware with what we call event-driven cameras. So those are cameras that are not, measuring the response of every pixel location, for every frame, but rather only detect the change that's happening, right? So those are cameras that can, with very, very small bandwidths, transmit a lot of information, very, very high resolution information by being only sensitive to change. I would say that, spiking neural network would make a lot of sense in this context because, these are the notion of timing becomes much more explicit when you relate timing to change and things of that sort. So I kind of like this line of work. And I think, from a hardware perspective, there's a lot of very good argument that's being made for building chips of spiking neural networks because they have very low power consumption. And it's true that our modern GPUs and are a disaster in terms of the amount of power consumption. So I'm all in favor of this line of work, and I think spikes makes a lot of sense in the context of minimizing energy use. What I'm a little bit more skeptical about is the idea that if you have spikes in one of our modern neural networks, the magic will happen, and suddenly they're going to start solving all kinds of problems that the current neural network won't solve.
Right.
And the reason I'm skeptical is that there is literally nothing in our modern formulation of neural network that would warrant that statement, in the sense that there's nothing for this neural network to explicitly use spikes or the timing of spikes. And so I think that's where my skepticism is. I do not think this is necessarily about whether we need spikes or not, because again, I think spiking neural network behave for the most part very similarly to rate-based non-spiking neural network. I think what we should be asking ourselves is what it is that we need to add in modern neural networks so that they are able to maybe encode information that potentially cannot be encoded in a simple rate kind of based model. And so, of course, I'm relating to a lot of old work and old ideas related to, oscillations, synchrony, the notion of, essentially multiplexing information in neural networks, and the possibility of binding, say, visual representations to objects through the notion of synchrony, for instance. And so, you alluded to the work that, we've been doing. This is very much my philosophy. The focus should be much more about how to extend neural networks so that are able to maybe leverage aspect of spike timing. Whether you do it with spike or without spike, to me, is irrelevant. And in fact, there's a lot of progress done right now in getting learning to work in spiking network, but because of very strong non-linearity and non-differentiability of this neural network, learning is typically a pain in the neck. And so to me, there is very little benefit in giving yourself the extra trouble of dealing with spikes, as opposed to coming up with formalisms such as, complex valued neurons and things of that sort that might enable you to build mathematical abstractions of what those spiking network can do without having to deal with the nitty-gritty details and the pain that comes along with dealing with spikes.
Well, yeah, I know that you're all in on oscillations too, and the importance, and it's a fairly straightforward. Spikes are fairly straightforward to integrate with the oscillation world, right, in a network. But your bet is building a biological constraint in a model, something like a spike, isn't by itself likely to lead to some insight that will later improve models. I mean, there's this balance, right? Because some biological constraints do lead to insights that improve deep neural networks, like convolutional neural networks and all the HMAX works, right? But they're a pain in the ass, spikes, but you can't do backpropagation, for instance. And so, we have to draw the line somewhere of what is important and what's not. And so for you, spikes in themselves, maybe computationally what they could give rise to, we could build in another way, and that would be just fine.
Just fine and much easier.
Much easier. Yeah, well, that's always good. Yeah.
Much easier and potentially. Right. So,
yeah. So what do you think is one of the, one or two of the missing biological constraints that you think would help break open a new frontier in deep networks? Is oscillations and synchrony one of them?
Maybe. Again, we have very, very preliminary work. There are old ideas that have been around. I think, the jury is still out. I think we need to do much more work. I think we need to come up with, kind of clearer, better demonstration of their benefits. We've been talking about a few examples. We've talked about attention. To me, it's exciting, which is one of the hallmark of kind of biological vision, working memory, attention, and interestingly for me, I think there is this trend in image categorization, even where attention network have now taken over, and so people in computer vision are starting to realize the need for attentional mechanisms. And in fact, beyond image categorization, if you look at the field of visual question answering, again, all of the state-of-the-art architecture incorporates some attentional mechanisms. The same way, I was very excited by the neural Turing machine. The people have started to show the benefit of having neural network that can read and write into memory, allowing them to solve tasks that would be otherwise, if not impossible, very, very hard for kind of standard convolutional neural network. And yet, I would say those attention network and, memory network neural training machines are quite different in their implementation or even algorithms with, what we know and understand about attention and working memory and memory more generally in biological vision. And so I think, there's still a lot of work that should be done, looking at the interplay between, this additional functions and with the potential for neuroscience to continue to inspire kind of computer vision. We've talked about spike timing. There's also a lot of minutia that goes on. A model of neurons, at least as implemented in kind of modern deep neural network, is we are talking about the scale from 0 to 100 earlier, where 0 is the Macunac and Pitt, and 100 is like the perfect model. With millions of compartments and all that stuff, capturing every detail of neural processing. I told you, I think we are at the scale of 20, being fairly optimistic. That said, it's not clear how much, so we know that there's much more happening. We know that computations happen at dendrites. There are all these kinds of nonlinearity that are far from being, even remotely captured by our simple models of neural function. And yet we don't know, what those biophysical mechanisms by individual neurons. And so, I think the jury is entirely out. I think more people need to get on board. More people need to try to ask and test the functional role of what those biophysical mechanisms. Some of them will probably be epiphenomena of biological minutia, but it's very likely that many of them would allow presumably neural network to go far beyond the capabilities of our kind of current state-of-the-art artificial intelligence systems.
Do prospective students, when they come, they want to join your lab, are they just interested in deep learning? And if so, is that a problem?
I hope not. So it's true that, most of my graduate students and postdoc come, like myself, from a more mathematical and computer science kind of background. But I think what unite all of us is a shared vision that, one, we care about biology and we want to understand biology better. And two, that in the process, we might still have something to contribute to the current field of computer vision and AI. So I do hope that, yes, they care about deep learning, but they do genuinely care about leveraging knowledge about neuroscience towards improving deep learning.
I've heard you lament the lack of knowledge these days from people coming into the field of just basic computer vision kind of functions from the old days. And where would you, if you were interested, there's so much to learn. If you were interested in positioning yourself to join a lab like yours, for instance, where the hell would you start? Do you have a clear path of how to train yourself up? Where would you begin?
Yeah, so I would take a blend of neuroscience, computer science, math, and psychology courses.
Just cycle between them, or?
Yeah, with a focus potentially on, the interplay between, taking enough courses in algebra and, machine learning and, deep learning, but also a fair amount of courses in receptive cognitive psychology, cognitive neuroscience. And, as a side note, that's, I think, part of the reason why, being French and, I live and work in the US and not in Europe. What fascinates me about the American educational system, especially a liberal college such as Brown, is that you have the flexibility of, really doing, just enough math, computer science, psychology, and computer vision during your undergrad that is specifically tailored to your own interest. And so I've seen, amazing undergraduate students coming out of, liberal art institution like Brown with, I so wish, I'm literally jealous, to get to that point. It took me, 2 years of class préparatoire in France where we did math and physics, mindlessly, followed by 3 years of graduate engineering school where, I did more math and signal processing and computer science, again, without necessarily understanding, what for. And it's only in my third year that I've specialized in computer vision, in image processing, discovered, artificial neural network, got really interested in the biological side of neural network, and then, fell in love with neuroscience and really wanted to contribute to that field. And so, 6 years before I got my first, class in a course in neuroscience, when, I have students at Brown who are able to take in their first year an introduction to computational neuroscience, where it's pretty unwavy, it's pretty but they are able to learn just enough to get hooked on the topic, and then being motivated to take the right amount of linear algebra that they need, the right amount of functional analysis, the right amount of neuroscience, psychology, so that they are really becoming experts in this field.
I think it's really underrated to always, if possible, have in mind the what for. Why am I studying this particular topic? Because it's going to make everything so much easier and faster. Yeah.
Absolutely. Yeah.
Is there anything that you wish you could have done differently besides having, that sort of tangible thing to grasp onto the whole time in your career? Because you've had a really, from the outside, it looks like a really nice path. You went and you studied in a very famous person's lab, and you've done great work, and you've gone on and started your own lab. Anything you wish you'd done differently?
I always feel already privileged, and I think I was, I had a fair amount of luck my whole life. I was, one of the big luck in my life was to get an internship in the Podio lab at MIT. This was my entry point at MIT. This is how I discovered research as done in the US. I was never exposed to research up to that point. And so I came into a lab where, there was a fair amount of mathematician, people, doing formal statistical learning theory. There was people doing good engineering, developing, designing computer vision systems for face detection and recognition. And then all the way to people collaborating very closely with monkey electrophysiology groups. And so when I arrived in the Podio lab, this was a complete eye-opener where, I'd never been exposed to this kind of interdisciplinary, research. I know that, Tommy gets potentially hundreds of emails per week.
Oh, yeah.
I don't think there was anything, massively special about my own little email. A lot of it was luck, the chance to being able to land in his lab and then, work hard, prove myself to be admitted as a PhD student, etc. So I would say, I had a fair amount of luck. To your point, would I do things differently? It's really hard. On the one hand, I kind of hated my undergrad, again, doing things for doing math, physics, computer science without knowing why.
Yeah.
And I just had to suck it up. And, at the same time, again, it's hard to imagine my life being as happy and seemingly perfect as it is. It's hard for me to argue that I should have done differently. But I am genuinely jealous for what I see our students were able to combine both, right? So not maybe do as much rigorous, studying in math and computer science, but get enough of it that they can also enjoy taking more, neuroscience and kind of vision classes and strike this balance between fundamental knowledge that you need to acquire to reach a certain level of, in science and research, but also doing research along the way and enjoying what they are doing in the process. That to me, it's invaluable.
Last question, and if you don't have an answer, that's okay. But I'm just thinking sort of, the idea of skating to where the puck is going to be, not where it is. You're mired. I mean, you obviously have like a vision long term, but you're also working on you're very in deep working on your projects. And that's going to take a long time and you're making progress. But then if you had to think like, what would I be working on if I just wrote a grant from nothing? And what would be the thing to be working on 15 years from now? You're going to decide, I think that X is going to be important 15 years from now. And I want to work up, it might not be hot right now, but I want to work up to my knowledge base to be studying that thing in 15 years. What is that thing?
I wish I had an answer, but to be honest, I don't. I mean, I
can't see the future.
As I said, back as a graduate, if you'd asked me back in the year 2005 that, what the field would look like in 2015, I would have been so far off. Yeah. I would have never predicted what we are seeing. The field is changing so quickly that, I would like to believe that neuroscience will be, continuing, in 15 years to still be and cognitive science will still be kind of sources of inspiration. So continuing to try to reverse engineer brain mechanisms will continue to provide some, but I don't have a good answer.
Yeah, none of us do. Thomas, thank you so much. So you're on Twitter. You're on Twitter at Serre. So you guys can find him there. And of course, at your lab website, I'll link to. And I really appreciate the time and good luck moving all your teaching online.
Thank you so much. This was fun. Thank you, Paul.
Brain Inspired is a production of me and you. You can support the show through Patreon for a microscopic $2 or $4 per month. Go to braininspired.co and find the red Patreon button there. Your contribution will help sustain and improve the show and prohibit any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thanks for your support. See you next time.
Mayday, mayday, we've left our heyday, searching the coffers for empty offers. I don't